Equipotential surfaces. Equipotential surfaces or equipotential lines are just a visualization tool. They illustrate where the potential is constant. Equipotential lines are actually projections on a two-dimensional page of a three-dimensional equipotential surface. It's just like a contour map. So if in a contour map where the lines are more, you know that the elevation is higher. Where the lines are spread apart, you know that there is a lower elevation. Same thing with potentials. Where there are more lines together, equipotential lines are together, that means it is a higher potential area. And as the areas go away, as the lines spread out, that means that the potential is going down. So some examples of what an equipotential surface looks like are these given here. So for example, for a positive charge that is a source of electrical fields, the equipotential lines are going to be given by these red concentric circles around them. Okay? For a line charge or an infinite sheet of charge, again, it's positive charge, so that means that the electrical field lines are going to go away from this charge. The equipotential surfaces are going to be straight. For an electrical dipole, it's going to be very interesting because the positive will be a source and the negative charge will be a sink. So the electrical field lines are going to be represented as they are in black here, whereas equipotential surfaces are going to be represented by these dashed red lines. So some things that you need to remember about equipotential lines: electrical field must be perpendicular to equipotential lines at all points. Otherwise, work would be required to move a charge along an equipotential surface, and so hence, therefore, those will not be equipotential. For non-moving charges, or for the static case, the surface of a conductor is always going to be an equipotential surface. Otherwise, charge would flow on it and it would not be a static case anymore. I also want to talk about how you calculate the field from a potential. So we calculated the potential from a field, right? The famous Ed equation. How do you do it the other way around? Well, in that case, you are going to call upon something called the gradient. So we know electrical field vectors point from higher to lower potentials. More specifically, E points along the shortest distance from a higher equipotential surface to a lower equipotential surface. You can use E to calculate V, which is VB minus VA equals integral from A to B, E dot dl. Okay? You can similarly use the differential version of this equation to calculate E if V is given. Okay? So in that case, dV will be E dot dl, or E dl if E is constant, or E will be equals to dV over dl. So for spherically symmetric charge distributions, E will be given by dV over dr. In one dimension, it'll just be Ex dV over dx, provided that our dimension is along the x-axis. It could be along the y or the z. It doesn't make any difference. And in three dimensions, again, it is going to be delta v, partial v over partial x, partial v over partial y, partial v over partial z, or E will be given by, in the vector form, by partial v over partial xi, where I is a unit vector, partial v over partial y, j, or partial v over partial z, k, or del v. This is called the gradient. Okay? Again, for us in this course, we don't need to actually be worried too much about how to solve it, but it is a very good idea for you to be to have seen it once.